Hello everyone, I'm Taihao Han from Missouri S&T. Today I'm going to present modeling hydration kinetics of sustainable cementitious blender use a data-informed nucleation and growth approach. Okay. So I think everyone in this room are familiar with concrete. Yeah, everyone loves concrete, cheap, provide good strength, it's most used materials in the constructions. So nowadays, the production of concrete is 40 billion tons per year due to the population increase and the demand for the urbanizations. The concrete production can increase to 6 billion tons at 2050. We know we love concrete, but it has an ugly side. So cement is a major component of concrete. So to produce cement, you need to heat your raw material above 1450 degrees. During that process, you will release a lot of carbon dioxide. Also, due to the decarbonation of the limestone, tons of carbon dioxide get emitted. Okay, so the cement manufacturer contribute 8% of the carbon emission every year. But nowadays, government advocates we want carbon neutralization. So the cement industry also want to achieve that goal. So, but it is hard because during the current technologies, we cannot change route to produce cement. So what can we do? Somebody said, okay, we can use the electricity to heat your raw materials. Yes, we can do that, but you need to remember one thing. 70% of your electricity is still generated by the coal or burning the fossil fuels, so it just transfer the carbon emission from one place to another. So we need more practical method to do that. So the more practical methods, we can use supplementary cementitious material, SCMs, to partially replace cement in the concrete. So that means we use less cement in the construction, we produce less, so we emit less carbon dioxide. So that is our sustainable blenders. Okay, so we can use quartz, limestone, like metakating to partially replace the cement in the concrete. We also can use industrial waste like flash, slag, waste glass. But to use like industrial waste, there is one issue. So the chemical composition between batch to batch for the industrial waste, they are different. So but we also know the chemical composition of the SCM can significantly affect your property of your concrete. So in that way, we won't get a consistent property of your concrete if we made concrete with like flash. In that way, so we want to develop some models that can predict the concrete properties made with the concrete made with industrial waste, so that we can adjust mixture design in advance and to get your qualified concrete that can satisfy the construction standard. So here you can see some examples like this type of flash affect the hydration kinetics like that way, but another flash you see the significantly different effects hydration kinetics. And also the compressive strength, another example. Even the same replacement level, you can see you will get a large variation in the compressive strength. So in our studies, we want to focus on the hydration kinetics. So for hydration kinetics, we can measure it from exothermic calorimetry, measure the heat release from the hydration reactions. So different hydration phase, you can see release different amount of heat. Also, that means if you have slightly different chemical composition different in your cement, you may get significantly hydration kinetics here. So if you want to do the modeling, so the challenge is to account for all the hydration mechanism in your model. Now let's talk about the hydration kinetics for the sustainable blender. So we want to add the SCM into our cement. So for the SCM, there are two types. One type, they're inert. We usually call it fillers. It's only physically provide additional surface for hydrates to grow nuclei. So in that way, basically no chemical effect from that kind of SCMs. But still, the different SCM can the effectiveness of grow nuclei, they're different. So like you can compare the hydration rate of the cement replaced by the limestone and quartz. So you can see the limestone is more effective in that way. So we also the rate of the hydrates is not a linear correlation. It's more like exponential here. So we want to account such correlations in our model too. So next type of the SCM, so it can chemically participate in the hydration reactions. So like silica fume or flash. So silica fume, the typical example is pozzolanic reactions. The silica fume dissolves silicate into your pore solution, react with free lime to form additional hydrate. And flash, you have some flash has very high sulfur content, so it dissolves a lot of sulfate ions in your pore solution that can significantly retard your hydration reactions. So during the modeling, it's hard to account for those chemical reactions here. Also, you can see here, so that is silica fume and the metakaolin have different reactions here, and flash that they all change the hydration kinetics. And we are not satisfied with binary system. We want to add more SCMs in our cement binder. We want to develop a ternary system. Okay, we add 2 SCMs, but there is another issue comes up. So that means not only SCM react with cement, but we also need to account for the chemical reactions between the SCM. For example, you can see the cement, limestone, and metakaolin, it can form the carbon aluminate. So, but we don't find that phase if we do not have these 3 components. So why do we want to focus on the hydration kinetics? Why do we want to model in hydration kinetics? So we think the hydration kinetics is one of the most important property for the cement and concrete. So if we know how much heat release, we can know the degree of your hydrations, and combined with thermodynamic simulations, we can know your microstructure, your phase assemblage. Also, you can see many properties they are correlated with heat release from hydration reactions. For example, compressive strength. If you release more heat, that means you form more hydrates, and then you have less porosity, higher strength. So in that way, if we can predict hydration kinetics of the cement, we can estimate the other properties for our sustainable binders. Nowadays, the most reliable model to predict to simulate the hydration kinetic is nucleation and growth rate models. So in that model we said the nuclei grows on the surface of the cement and SCMs, but that model only account for like single product. It only have a constant density, but in the reality we know it has many hydrates. Also the growth rate. So we know the growth rate of hydrates changes with your ion concentration. Okay, but this model cannot do that. It only have a constant rate. But still, this model can, with the input of cement, SCM, water content, and a specific area, it can simulate the hydration reactions. Okay, here. And later, researchers developed another model they called modified phase boundary nucleation and growth rate model. So this model solve the issue I mentioned previously. So this model can account for the multiple products here have different densities. Also, the growth rate of the hydrates get changed with time here. So you can see the graph here. So the blue line is from the classical models. You get a constant growth rate, but you cannot get an excellent feed here. it can capture peak, but you cannot get the excellent fit. But the red line is a modified one. You have the growth rate change with time. So you can see the model can capture the entire hydration kinetic profiles even at the very beginning of the reactions here. But still, those nucleation and growth rate model have one big issue. So if you want to use these models, you need to know the growth rate of your hydrate. So the growth rate of hydrate can be measured by the experiment, but that means you only can use the nucleation and growth model to a known system. If you have a new system, new cement benders, the nucleation and growth rate model cannot predict the hydration kinetics unless you give the growth rate of your hydrate. So, but we still want to use that model. We know that model is reliable. What can we do? So we can combine that model with machine learning. So we use machine learning model to predict the critical parameters used by nucleation and growth rate models. So machine learning model is a kind of artificial intelligence, and it has been widely used in the cement chemistry to predict cement concrete properties. So to use that model, first you need to do some experiments and to measure your properties, and then you get a training database. So to train your models learns the input-output correlations from your training dataset, and then leverage such correlation to a new dataset. So the model can produce a prediction here. So in our studies, we use the mixture design of the cement and also the physical chemical property of cement, like the specific surface area of the cement and SCMs as the input. So the machine learning model to predict the growth rate of your hydrates, and then we implement the growth rate of hydrate to the nucleation and growth rate model to produce the heat flow rate profiles here. So our SCMs include most common SCMs, so quartz, limestone, silica fume, metakaolin, also 10 flashes. Okay. And that is a major equation we use in our nucleation and growth rate model. So first we know the degree of hydration from the calorimetry profiles, then we calculate the XT here. And then after we get XT, we use XT to calculate the GOUT. The GOUT is growth rate of hydrates. So first we calculate the growth rate of hydrates for the training data set. So we use that data set to train our machine learning model. And then we do the predictions, and the machine learning model predicts the growth rate, and then we implement the growth rate hydrate back to that equation to calculate the hydration kinetic profiles here. So on the right, we show here, so if we know the growth rate of a hydrate, you can make a very good simulation for your hydration kinetics profiles. Also, in our model, we use effective surface area, that concept, that parameters to control the surface area of the SCM, so that can compensate the chemical effect from the SCM. For example, the limestone or quartz, they are inner, so the effective surface area is 1. But for the flash, we know we have a lot of sulfide that can retard hydrations, so we set the effective surface area at 0.2 or 0.3, depend on the sulfur content. So that can eliminate some area that to grow nuclei, so that can compensate the chemical effect here. Now let's talk about machine learning models here. So in this study, the random forest model is used. Okay, and then we can see these two profile here. So the first profile is the heat flow rate. So we can use machine learning model to directly predict the heat flow rate, but it's very difficult for machine learning to do this prediction. So you can compare the bottom one as the growth rate of hydrates. You can compare compare their two profiles. So you can see the heat flow rate profile is much complex than the growth rate. The growth rate profiles. You can see the peak, the inflection point, the trend get changed directions. So it's very complex. The machine learning can capture some trend, but not all of them. But the growth rate profile is much easier. You very high at the beginning and then decrease. Very simple structure. Machine learning can easily capture it. So here is our results. So after we predict the growth rate, we implement in the nucleation and growth model, we get the result. The blue line is the result from nucleation and growth rate model. Yeah, and the green line, the green dot is the prediction directly from the machine learning model. We use machine learning model directly predict the heat flow. You can see the green dot cannot capture the peak here, but the result from nucleation and growth model, you can see this excellent prediction. Also, the nucleation and growth model solve another issue. So machine learning is a data-driven method. So it's a data-driven method. It may violate some material laws, but if you use nucleation and growth model to regulate your final output here, so you don't need to worry about that issues. And next, here's some other application of machine learning. So first you can combine with game theories, then you can rank up your variable importance to know which inputs are important, and then develop some analytical models. So that's very important for some new materials that's not well studied, but it gives you some guideline for research, give guideline for researcher to find some correlations. Also, it can predict property for different other type of material like glass, ceramic here. Another amazing thing of the machine learning model is optimization. If you have know the target properties, you can use machine learning model to optimize your mixture design to satisfy your target properties. So conclusion in the end, so use SCM to partially replace cement is an emerging solution for reduced carbon emission in the cement industry, and we can use nucleation and growth rate model to reproduce the hydration kinetics of our sustainable blender systems. Also, especially combined with machine learning models, we can predict the hydration kinetics for the new system. Yeah, that's all I got today. Thanks, guys.
Thank you very much for your presentation. In one of the slides, there were a good match between heat flow rate of the, was it like a real experiment? The red line?
Let me see. This one?
Yes.
So the red line is real experiment.
Real experiment.
Yeah, measured from calorimetry.
Yeah. So actually, because something that this is like the test we did a few weeks ago. If you test, if you get a heat flow rate of your sample, for example, calcine clay mix. If you repeat one mix design for 3 times, you get different experimental results. So I was wondering why there is such a good correlation between heat flow rate and MAE. For experiment, there is a huge variation. That's something we saw. So I was wondering how we can get good correlation.
So actually, we did. So for our system, we have repeat many of the systems in our studies, but we do not see a very big difference between each measurement. So we can discuss your issue later, but in that way, so we won't see a It has some variations. That's due to the measurement errors here, but we don't see very big variations.